My name is Naftali GATHIMBA, for those who might be watching this video later who are not in our class. And I am a lecturer at the Jomo Kenyatta University of Agriculture and Technology, now handling structural engineering area. Now, we started the lecture series 3 weeks ago on Introduction to Finite Element Methods, or what in some books or some courses we call it matrix analysis of structures, because we are using matrix method to solve or to analyze our structure. And we've covered the introduction in lesson 1. You can watch it later on. I'll leave you can go to the link. You see, the description, you can see the link. We covered a finite element as a simple and a unique finite element called the spring element, which we said this was for analysis and for understanding on the processes involved in formulation of equilibrium equation or finite element equations. Now, today we go to a third element or second element in lecture number 3 that we are calling the bar element. Now, this is an actual element that you can use in a structure. Remember, the spring element was for illustration purposes, though there are some supports that we treat as springs, but of course, in real life scenario, construction of structures, we don't have springs. So the bar element, what is this element? So we have an elastic, it's always called an elastic element. Elastic meaning obeying Hooke's law, that the applied force will always be equal to all proportional to the elongation or the deformation. Now, it's similar to the spring. That's why we started with the spring for ease of understanding. And for your case or for what you have been covering, you have had the issue of a truss. Okay, so don't worry why I use the truss so much. It's because I know this is the one that you have covered all the way from theory of structures 1, and it's also easy to comprehend, because for the truss, there is one assumption that we make, and that is okay. Sorry, this should be the roller support on this side, and this is the joints are pinned. So with the joints being pinned, it means if you are considering this member, I call this member 2 or element 2 in our finite element analysis, this element can only carry axial loads. Okay, so it means no moment, no bedding, because if we fixed here, if it was fixed here, then we know that bedding will occur in this member. But now when the joint is pinned, there is no moment that will develop, no rotation that will occur at the joint, because the joint is free to rotate. Yeah, that's a meaning of the hitched or pinned joint. And again, only axial loads. That's only axial meaning along. Is this our member here? This is our member 2. Only loads that along this direction, along the length of the member, are considered. We do not have the transverse load. We do not have transverse load here. So when you apply, that's why when we apply the load at the joint, when you are doing truss analysis, then we solve the forces to the forces will be carried, or the axial forces will be transmitted along the length of these members, right? So this is very useful first when we are dealing with both 2 and 3-dimensional cases. Remember the spring element, we said this is a spring, and then we said because we are only considering the axial deformation in the direction, let's say u or x. So this is node 1, this is node 2. So at each node, we have 1 degree of freedom, 1 direction, or one form of deformation that can occur, and that is the elongation or contraction. Now, so for a spring element, we say it's a 2-node element. It's a 1D with 2 nodes, and the degree of freedom at each node is 1. But for a whole element, the degree of freedom is 2, because we have U1 deformation at the deformation U at node 1 and at node 2. Same case for the bar element. But now we are going to advance and we are going to see the other steps. Remember, we said for the spring element, we cannot use it for analysis or stress analysis, okay, directly. So, but now here, remember, we have the steps that we do follow. If you are together with me, I gave you 8 steps that we follow when we are doing a finite element analysis. And the first step, once you discretize, you break down. So once you specify these are the nodes usually will come at the intersection of joints, intersection of different members, or the change of geometry. For example, if you have a bar element like that composed of two different member sections, and then maybe it's fixed on this edge. So it's logical to assume that the node 1 will be here. Here at the stage of geometry, you have node 2, and of course at edge here you have node 3. Another assumption or another possible location of the node is when we have applied load here, but not always necessary, but you can make a node here. So you can say this is node 1, node 2 where the load is applied, node 3. We are going to see when we count the beam element that not always that when we have a node. But for our case now, assume that the location of node, if we are not given where the nodes are, you are just shown a structure. So first of all, the direct and most obvious assumption is that at the support there's a node, at the intersection of two members that's a node, and at the change of geometry or cross section that's a node, and then application of the load. Now we are talking about the 8 steps that I gave. We said after discretizing, and then you select the type of element. Already now we have selected the type of element, which is the bar element. You need to go to the step 2, where you need to define the displacement function. These are the steps we said we could not, we did not go through them in the spring element. Spring element was a stripped down version of the bar element. And then step 3, we need to define the strain, displacement, and the stress-strain relations. From there, the other steps I think we had out where you have to determine the elemental stiffness matrix, and then you get the global stiffness matrix, and then you get the global finite element equation. You start solving for unknown degrees of freedom, which in this case, because you are using the direct stiffness method, the displacement, force displacement method, so it means that we are talking of the displacement being the unknowns. And after that, now you solve for the elemental strain. That is, you start recovery stage to get what is the internal stresses and strains in the member. And finally, you need to understand your result. So in this case now, we are going to look at the second step. We have the element. So for us to go to the stage of getting the global or the finite element stiffness equation and the finite element equation for this member of this element, we need to get the displacement function. But before then, there are some assumptions that we have or we make when we're using this member or when we're using these bar element. One, we assume that this is is geometrically linear. That we assume that the member, the bar is geometrically linear. So this one now simplifies our linear. This will simplify our working because what we are saying is that our member, our section here is like this. So we are negating or we are eliminating the cases whereby we have curved bars because it's possible. We have curved beams, we have curved section in structures. So in this case, we are limiting ourselves to only cases whereby the bar element is linear. Number 2, you assume that the material obeys Hooke's law. Okay, so the material that constitutes the bar element, it obeys Hooke's law. So in this case, the Hooke's law, that is, because we are considering linear elastic bar, an elastic element here. So elastic bar. So we are considering as the stage where force is directly proportional to the deformation or the elongation. So we are considering the linear stage. If this is the curve, if this is the deformation, this is the force. So we are considering the case. For the bar element, we are considering up to when the force of the deformation are directly proportional. Then the other assumption that we make is that forces are applied. This is obvious because remember the bars, you can consider the bar is also called the truss element. And we are going to see the difference between, I'm going to just show you the difference between the truss structure and the truss element. So forces are applied only at the nodes or only at the edge of the bar. Oh, you have this note, so I think I should not be giving all this. But anyway, for somebody not in our class, it's good you have this. So the forces are applied at the edge of the bar, and by this, you get something like this. If it have many elements here, let me just simplify it. This is a three-member truss, three-member truss structure. So this is one member, two member, and the third member. So this is a structure constituted of element. So this element here from this node, let's say this node 1, 2, and we say that for element you circle here to differentiate from the node. So the member, the node 1 to constitute or it's defined the domain of the element, truss element, one of the truss structure constituted of all the three nodes. So the element is just one member. And that's why we are also referring to it as the truss element. Now, the final assumption that is made is the bar will support only the axial load. So bar supports only axial load or axial loads only. So what does that mean? So this is like we are taking you back to analysis of trusses, the truss where you are talking of the method of resolution at joints. So in this case, what we are just saying is that no torsion, no bending will occur, no shear force will be transmitted to the element via any nature of the connection, because the connection are pinned. So it means that no torsion, no rotation. I mean, no movement, fixed movement will develop at that node. So those are the assumptions that you make when you are using the bar element. So let's see now, we want to go and define or specify, start developing or formulating the finite element equation for this element. So consider a case where we have a uniform prismatic bar, a uniform prism. So prism, it could be, the cross-section could be changed. We could have a rectangular prism, we could have a circular prism, we could have what type of another prism you can have. So maybe that's the cross-section, and then we have, these are the edges. So this is the prism we are talking about. So we are saying is 3D. So this prism, now we are not concerned about this dimension. This dimension here, we are not concerned about the thickness. Yeah. So this thickness T is not of our concern. So we are concerned about this length, the length here. Oh, my drawing is clumsy. We are concerned about that length only because it's a 1D bar element. It's like a line element. Now, with that, the node 1, and therefore we can take arbitrary values because we'll be having different bar elements with the node. Maybe one will start with from node 5, 6, another one from node 8, 9. So in that case, we can say node ij, where I is, we can always consider I to be less than j. That is, I is the lower node. Okay, so this one, we talk of the node 3, 4, 3 being the resonance. And then there is the internal nodal forces, F. We say the small f, letter F, represents the nodal forces, internal or internal or nodal forces. So this is at node I, Fi and Fj. We have the internal forces. Then the length is given. Then the direction we are considering, remember, is in one direction. So direction U or direction X there. And we can have external force F, but for now, let's stop there. And then the property. Remember the constitutive material properties? So AE, these are the ones that will help us define the relationship between the stress strain. So the cross-section of the bar is given. So the other dimension that we disregarded, the thickness and the breadth, is covered by the cross-section. And of course, now the material behavior is given by the A. This A represents geometry. Okay, this one represents geometry. And then this will represent the material behavior. And the E, Young's modular. E is Young's modulus. And these two, the combination of these, this is what gives about the stiffness, the rigidity of our structure. Remember, for the bar, for the spring, the K, stiffness K, was given by just the stiffness of the material itself, because we are not concerned about the stress analysis, so we did not look at the cross-sectional area of the bar. Okay. So with this, we have defined what is the length, cross-sectional area, elastic modulus. We have defined the displacement U. Of course, U is equals to UX. Okay. So U, the displacement U, varies. By putting X here, it means the displacement will vary along the length of the bar. What do you mean? Let's assume that we have that as a fixed edge. This is our bar. So this is a fixed edge here. So if we apply a load here, or let's consider that, so that we remain, I don't want to go to the cantilever, because at this stage, we are talking of the bar element being a carrying axial load only. So let's consider a case whereby we have, that's our bar, and then maybe there is a load suspended here. Okay, so that the force or the applied load is in the direction of the length of the member. So in this case, of course, the displacement U, and we can measure the length of this bar from here to here is L. So from here to any section, any point, we can define it as X. So if this bar will elongate, if because of this load, this bar elongates up to a certain point there, okay? So what we are talking about here is if we are at X, this point, so for the elongated bar, maybe this point would be here if we had put a marker, and we can be able to define the elongation. So the elongation for different points can be given, or it can be defined. So we are saying the displacement U can be defined for different points, U, X. Maybe at this stage here, you might not see it clearly, but if around me, although I did not want to use this, let me go ahead with the member that you are so familiar with, the cantilever member section. So in this case, if there is, because of the load, there's a deformation, something like this. So from any point, the total length is L. At any point X here, you can see the rotation here is different from here. So we are saying at X is equal to a certain value, we can have a different or same deformation. So that's the meaning of why we are defining U in terms of a UX. And again, the same thing with the strain. E, or the strain E, at any point, EX can be defined. And of course, the stress can be defined for at any point. So with that, then we go ahead and say, these are the definition that I was giving you. Then the first step that you need to do, or the second step, because you already have defined, we have discretized our structure, we have broken down stage. Then we have defined the element type, we have selected the element type, which is a bar element in this case. Now we need to go to step 2 of the 8 stages. We need to select a displacement function. And to do this, we can assume the linear, that displacement varies linearly around the axis of the bar. Okay, so why can we suitably assume such? Because we said in the assumption, we said the bar obeys Hooke's law, and we are talking of an elastic bar element. So if it obeys Hooke's law, force is equal to the same as displacement. That is, let me give, I like using sketches for ease of understanding. So if this is the case, force is direct proportional to the displacement. So it means as the load is continuing being applied, the displacement or the deformation along the axis of the bar can vary linearly. And as we know, the linear equation y is equals to mx plus c. So we can assume an equation of that form. And in this case, so our y here, so this will be the y is equals to mx, the gradient times x, plus the y-intercept c. So we are just using the different notation here, the constant a1 and a2, and then x. So we have a linear equation. So from there, what we need to do is, can we be able to get what are these constants a1 and a2? And to do that, we need to express them in terms of the values that we are given. So in our case here, we need to express this displacement in terms of the value or the displacement u in terms of L, because what is varying, the variables here, parameters that we have, is this x, the distance from the node I up to any point, and L, the total length. So to do this, at this stage, this part you don't have it in your note. You only have the equation number 3. In your note, you have equation number 3. So we are deriving that equation number 3. So in this case now here, let me clear that. So we have already stated here that this is our equation. This is our assumed linear relation, that the displacement varies linearly. So we have a linear equation. And then you need to express, or we can express, the constant a1 and a2 in terms of nodal displacement. Remember, because we said we interpolate between the nodes. So we want to define our displacement in terms of the displacement at this node 1, node 2. Can we get the displacement or at any one point by interpolating between the known the displacement calculated at the node? So assume, or this is now in deriving that or getting the constant. So at node at x is equals to 0, at the starting point here, in this equation, if you substitute x is equals to 0, you get u0, which is the same as u0 is the same as u, or displacement at node 1. u1 is equals to a, because this part collapses. At x is equals to L, at this now other node L, when x is equals to L, you substitute L here. So you are going to get u1, which is equals to u2. You're going to get this as u1, because we already found a1 to be u1 in the first step, u1 plus a2 L. So, and we can make a2, the other constant, the subject of the formula. Therefore, a2 becomes, just to make a2 the subject of the formula here, you have u2 minus u1 over L. And therefore, our equation, so you need to substitute what is a1. What is a1? a1 here we found it's u1. And what is a2? a2 is u1 minus u2 minus u1 over L. So this equation, or if we now we factor out the displacement, so u1, u2, this is what we call the displacement function. We have come up with the displacement function for a bar element. So this is how it's varying. So at any one point between the two nodes, you can interpolate. You can be able, because remember, finite element method is an approximation method. So we are going to get exact values at the node. Any other point within the node is about interpolating. And we are interpolating from the known values of u1 and u2. Remember, u1 and u2, you are going to calculate. Like the example we did, we were able to get the displacement at the node. So if you want to know what is the deformation at any other point, we interpolate, and we have already come up with a displacement function. Now in your notes, this is the equation you have. The equation I have indicated here in red is what we have. But I hope you appreciate the steps that we have taken in deriving that. It's a simple step, easy to follow. I look at it again. All right. Then let's see now. We have the displacement function. So now I'm writing it here for ease of reference. Step 3, now we need to define what is the strain, displacement, and stress strain relations. Remember, we are following the 8 steps. Always, this is the process of finite element analysis. No new steps will come into play. It's all about varying with the different elements. Now, of course, this is dialect. the displacement relation, strain, it varies, or the du over dx. And the stress strain, you know, of course, strain is equals to Young's modulus times strain. Stress is equals to Young's modulus times the strain. Because of the issue of material-based Hooke's law. And of course, now this is why du over dx, if I might ask. What is the strain? Strain is erogation of a original length. We know that, right? So at any one point, this is a generalization when you have a continuous system. So in continuous system, now we can use the derivatives du over dx. But remember, the strain is equals to, it will always be u2 minus u1 over the length. Okay, erogation of our original length. I hope I've not lost you there. So these are the definition of the stress strain and strain displacement relation. So now we move to step number 4, derive elemental stiffness matrix and equation. And this one, I'm happy because we started with a spring element, so it's very easy to follow. Okay, so I've just now projected the same thing that we had in the previous slide. And so this is what I've given you in the previous slide. And then for discrete systems, for non-continuous system, we can write it in discrete form. That is the displacement erogation over, or the displacement over the initial, the overall length. And of course, erogation, we can use the capital delta. Again, stress is equals to Young's modulus times strain. And you can substitute now, this is your strain here. This is repetition of physics. Young's modulus times strain. But we also know that stress is equals to force over area. Okay? And F, stress is equals to force over area, and F is force in the bar. So if you look at equation 5 and 6, they represent the same quantity. And therefore, you can equate equation 5 and 6. This will be EA over L is the same as F over A. If you make F the subject, remember the form of the finite element equation is equals to F is equals to K times displacement or deformation. So here, F will be equals to, you take it to the other side. Is it? This one becomes, sorry. Is it, this is not A. I'm sorry for this. This is deformation. Okay, so you'll have F is equals to EA delta over L. So you can see delta is here, is represented by this capital delta. And then this part is the one that constitutes the stiffness of the bar element. So you can see the bar element, as I was saying earlier, the stiffness or the rigidity will be a factor of the material characteristic, the Young's modulus, and the geometry. You see now you have A and L. So those two, the material and geometry, now defines the stiffness of a structure. Now, if you look at this bar element, we say it behaves almost like a spring element, and you can see it very clearly. F is equals to KB, and in this case, K, the stiffness K for the bar element will be given by EAL. Remember another thing, just for your understanding, this should be having, or you should have this at your fingertips always. We said K for the spring element is equals to K 1 minus 1 minus 1, 1. That is the stiffness of the bar element, of the spring element. So for the bar element in this case, this K becomes EA of L. EA of L, the other things remains the same. All right. And now this is what we have in the next slide. This is F. Okay, this is what we have derived. We have found what is the stiffness of the bar. And therefore, the elemental stiffness matrix, K element for the bar element, you can write KEB or KBE, is equals to same like the spring element here, right? Same like the spring element, but now the K being EA over R. Very simple. Finally, to get the elemental finite element equation or the equilibrium equation, we just need to introduce the vector, the force vector and the displacement vector. This is what we have here. You introduce the force vector, the nodal forces, F1, F2, because we have F, talk of F being equals to K times the displacement. I remember always to put the braces, square bracket, braces. Okay, so this is the K, all this part is the K. Then we have the displacement, nodal displacement and nodal forces. So you have derived the elemental finite element equation for the bar element. Next, we need to go to the other stage. And I know now you have already refreshed your mind. The other stage will be, we need to, okay, before I go to the other stage, let me mention something. The other stage, of course, will be now, we have the stiffness matrix for the bar element at the local scale. So we need to, for the overall structure, the assembly, we call it the assembly stage. Now we need, for the different finite elements, bar element, we need to assemble the global stiffness matrix or the overall stiffness matrix, and then we get the overall finite element equation, so that now we can solve for the nodal unknowns. So for us to have global, we cannot use one element. I mean, for us to solve the equation, to have a finite element equation for the structure, one element is just a part extracted from a structure. And we said, because there are no boundary conditions defined, we do not have a solution. The matrix here is non-invertible. Okay, so that means we might not be able to get the determinant until we define, or to get the solution until we define the boundary condition. Okay, so in that case, we need to have an assembly of different bar elements so that we can go to the assembly stage. So it means from here, I'm going to drop now this one element, and then I have to go to a case where you have more than one element. Now to do that, we have an example, that is example 2.1 that we are going to solve. But before then, I need to give you some few notes that you need to note, which are very important. And we are going to see them even later on, for it applies for all other types of elements. Something we call, number one, we call shape functions. Shape function, you can write it somewhere, because again, this part you don't have it in your note. And I did it intentionally. Not that it was in your note, I did not remove it. I said the notes I gave you for last year, but I'm upgrading them. And I'm trying to push you to the new curriculum that we are developing. So these are the additional materials that shall be incorporated there. So the shape function, what is a shape function? These are the functions that we use to interpolate by assuming the displacement of a field within the element through interpolating of non-nodal displacement. Well, that's a mouthful statement, but let's see with the example. Remember we said the only values that are known is at the nodes, right? And the displacement function that we used was to help us interpolate or to get the deformation at any other point within or in the middle, within the nodes, right? So if you look at the equation we had, ux, this is now our displacement function that we defined, is 1 minus x over L, u1, plus x over L, u2. If you look closely at this equation, you can be able to see that there is a value here, a constant. No, it's not a constant because x is varying, but there is a coefficient before u1, and there's another coefficient before u2. That shows that displacement at any point within this bar, maybe displacement at this point, will be determined, or it's a factor. It's a matter of, it's related with what is the value, how much we are how far away are we from this node and from this node. So at any one point, there is a coefficient that determines what is the contribution of the displacement at this part due to the displacement at this node. And this one we can call it N1 and N2. So this one we call them the shape function. So N1, this is just this part. This one we are calling it N1 and N2. And this shape function, you can sketch them like this. If you look at this equation, when x at the start point here, when x is equals to 0, this value is 1. So if this x is this is 1. So and when x is equals to L at this node, so L over L, this is 1. 1 minus 1 is 0. And we know a linear variation. So this is 0. So this one, the shape function N1 is equals to 1 minus x over L. This is the shape of the shape function N1, and again the shape function of N2. Now I'm sketching quickly because we know when x is 0 at this starting point, this is a point 0. Of course, this is the total L length L. So this will be 1, this will be 0. Because if you substitute x is equals to 0 here, this collapses. If you put x is equals to L, this becomes 1. So what we are saying is that these two act together. The shape function. These are the interpolating function that we have assumed a linear relationship. Now we know there is a function N1 which relates the displacement from the node N1, and there's from the node 1, and there is the interpolating function relating again node 1 and 2, but with heavy weight. Okay, good. That term is good. We can talk of them as the weighting function. The weight, depending with the distance from each node. What is the weight N1 and N2? These are what we call the interpolating or the shape function. And why do we need them? It's because it's difficult or very impossible at times to obtain a closed form or an exact solution. Of course, we say for finite element method, we're going to get exact at the node. Therefore, we assume a shape. And in this case, when we are starting, we assumed a linear relation. So our shape function varies linearly. And the contribution of them both, if we add this one here, and if you can see it clearly, it will be like this. So this is the node 1, this is the node 2. This is N2, and then this is N1. So you can see there, as we move from node 1 to node 2, the weighting function N1 continue decreasing, such that when we are at point, or we are at node 2, the contribution of node 1 is insignificant. The displacement at node 2 is independent of displacement at node 1. Another thing to note is that the values of the shape function varies from 0 to 1. Of course, because we assume the linear relation, that's why we have a straight line. We see another case with higher order element where this one can be cubic. And when it's cubic, it will give us, no, not cubic, quadratic, or when it's higher order, it might give us more exact solution. Because remember we said, we are kind of estimating a case whereby we have a circle, and then we want to get a perimeter. We have the different bar element. So this is the center maybe. So if this the displacement function here that we defined was not linear, so maybe it was quadratic, so it could go something like this. You can see at this point it's more closer to the exact solution than when we have used a straight or a linear bar. Okay, let me not go far away from, deeper into that, but I wanted you to have a touch or a feel of what are the shape function. It's just our displacement function. Now we have extracted the interpolating function within what you call the shape function. Number 2, a note I want you to see is strain displacement matrix. Okay. Now, the strain displacement matrix, you might be told to define stress, or you find stress defined, and I think this one you have it in your notes. Remember, we have this equation, our displacement equation, this one. Okay, So this is U. I don't want to give you the equation you don't have. Okay, this one you have it. We are using 1 or I. So in this case, if you have our displacement equation, ux is equals to 1 minus x of L. This is what we had in the previous slide. U1 or ui plus x of L u2 or uj. Okay, this is the displacement. So the strain, remember we said the strain is equals to change in the displacement or du over dx. And this one will give you, if you derive, if you find the derivative, differentiate, if you differentiate this, I don't know whether you can help me to get the derivative of this. We are going to get something like, I'm looking at where I've given you that. I don't know whether I have given you that note. Yes. So what you are going to have, let's write this in matrix form. Okay, because we are differentiating in terms of x d over dx. So let's have the equation in terms of x instead of u. So you are going to have, of course, this you open up will be u1 minus u1 x over L plus x over L u2. Or in short, you are going to have 1 minus x over L u1 plus x over L u2. Okay. So with this now, we can derive this. This is not differentiation. We are still saying this is, we need to get d over dx of this. But at this stage, to avoid confusion, this is just u. This is u. So I can remove this part. And we have our expression here. That is u. We have ux. We have expressed it in terms of x, where is 1 minus x over L u1. You can see I'm solving equation in class. So you also need to be doing so. We are just deriving. I mean, deriving the what you call the strain displacement matrix by doing from first principles. So I've just moved that one up there so that you have it there. We have a working space. So from here now, we can be able to get what we call the strain, which is equals to du over dx. So if you differentiate this, you are going to get, this one will be minus 1, because it's 0. This is minus 1 over L u1 plus 1 over L u2. Let's write it in matrix form. This will be minus 1 over L, 1 over L, u1, u2. This is you put the braces there. So with this, so we are saying strain is equals to this matrix here times the displacement. And this one, this part, we use a letter, we can denote it by a letter B. And of course, now this one will be U. So you have B. We have these braces. So remember, even this is a row vector. We know as we go to higher node, we can have more nodes. It might be in a rectangular matrix. So we are just putting the square here. You can also put the braces. So our strain can be defined by B times U. And this B is what we call the strain displacement matrix. Okay, or the displacement matrix. All right, and therefore stress, which is equals to Young's modulus times strain, can be given. Now this one you have it in your notes on page, I think 41 or 42. This will be given by strain times the displacement, the strain displacement matrix, of course, times the displacement vector. We are going to see that through example. So those are just the two notes I wanted to note about the what we call it, the shape function, and note 2 on a strain displacement. So that was like a breather. It was like a breather from our steps, because we had covered up to step 4 or 5. Step 4, where we hold for one element. So now we are going to see through having more than one element, how we can go to the assembly stage so that we can get the global finite element. First, the global stiffness matrix, and then the global finite element equation. Right. So let's see with this example. Now, this is example in your note. You are given a 2-bar assembly, which is loaded with a force P at this point, and it's constrained. So these are is restrained at this end, as shown in the figure. So you are required to find the stresses in the 2-bar, the stress on this bar and this one. So the first step, breakdown, and then you select the element type. So the breakdown, to break down, we have to define what is the extent, the domain, the scope of our finite element. And in this case, we say at the support, this is when you can say node 1. At the point of change of geometry of or application of a load, we node 2, and of course, this support node 3. So for a start, we can have that. Therefore, this becomes element 1, and this becomes element 2. So we have now broken down our structure to 2-bar element. Of course, the statement is made 2-bar assembly. You can make it further, but you see why no need. You not get more refined results by having more than that 2 finite elements in this case. So with that, then we move to the stage of now the steps that we always have. So we move first. The stiffness matrix for the finite element. So now this is our structure. I have shown the node. We have specified the node 1, 2, 3, and the bar or the element 1 and 2. And as you can see, the cross-sectional area of element 1 is twice that of element 2. They have the same modulus of elasticity. Okay. So first, elemental stiffness matrix. This is quite easy. So K, remember we say this EA over L, 1 minus 1 minus 1, 1. So EA, remember the A here is 2. So this one here will have, in this case, we'll have 2A for the element 1. And therefore, for element 2, we are going to have the same case, but now AE over L. You should be writing this in your note. 1 minus 1 minus 1, 1. But the beauty of this now online thing is that you can always come back here and refresh. So that's the elemental stiffness matrix. Step number 2, we need to get the combined stiffness matrix or the global stiffness matrix for the overall structure. Remember the superposition principle? So I was encouraging you to really practice on that, so that you do not, the force displacement, the force equilibrium equation method, that is going all the way back from the basics. But for superposition, because of the principle of compatibility, we know that the displacement at the same node, like node 2 here, the displacement at this member is the same. This member is the same at this node. So we can use the compatibility expression. So what you just need to do is now get the overall, the global stiffness equation. So you know there are 3 nodes. So you can prepare your matrix there. And this is why I was saying use pencils, so that you can note here on this edge, you can have U1, U2, U3, U1, U2, U3. Remember, these are not part of the matrix. So this is just to guide you. Okay. Remember these lines I'm drawing very faintly in a pencil so that they don't, at least at the end of it, you have just the matrix in its standard form. So what you're just going to do is, this we know is U1, because K1 is 1, 2, U1, U2. And this is U2, U3, or no 2, no 3. So you just need to come here and say, at this cell, U1, U1, we have U1, U1 here. This is U1, U2. You have U1, U2. Then U1, this one you have an element U1, U1 for the element 1, U1, U1. But in the element K2, we do not have U1, U1. So this one remains 1. Remember, here, outside here, for that to combine this and this, you know, this is AE of L. So the common factor here, AE of L, we can put it out. So if you put this one out, this one now I'll do it for ease of our working. I'm going now to factor in 2. So that we'll have, this will be 2 minus 2 minus 2, 2. You see, now we have common factor AE of L, AE of L, which we can put it out here. So that now this value here is not 2. So this not 1 is 2. So this one will become we have this one as 2. So if you come to this now element, or the element of this matrix, let me not use the word element. Remember, in matrices we can talk of element, but let me talk of is it a member? Yeah, so that you don't confuse with the finite element. So in this cell, let me use the term cell. In this cell, U2, U1, you come here, you find the U2, U1, you have minus 2. U2, U1, you have 1. So it's minus 2 plus 1. Okay. Minus 2 plus 1. Sorry. This is U2, U1. U2, U1. U2, U1. Sorry. I'm getting lost here. This is not U1. This is U3, U2, U3. You see, if you are not careful, you make a small mistake there. You can get lost somewhere. You can start adding values which are not related. Okay. So U2, U1, you have minus 2. U2, U1, you don't have anything here. So this one will be minus 2. So and so on and so forth. You can go ahead and fill all the other cells. So like now, if I can just jump to this one, this point here, this is U2, U2. So U2, U2 here is 2. U2, U2 here is 1. So this will be 2 plus 1. So this will be 3. And therefore, we are going to have our global stiffness matrix. The global stiffness matrix, I hope now you are working it out. You are almost through with it. We are going to have K is equals to 2 minus 2, 0, minus 2, 3, minus 1, 0, minus 1, 1. You can confirm that. This is the global stiffness matrix. So when we come to now the global finite element equation, you just need to introduce the force vector and the displacement vector. And remember, when we have assembled more than 2 elements, we are talking of the assembly at the global scale. We are talking of as the finite element equation of a structure, not of that element. So now you are not going to see the small f talking of the nodal forces, because we are talking of combination of different elements. That's why we go directly to global stiffness finite element equation. So you're going to see capital F's. And this is given in the next slide as shown here. So this is the finite element, this is the finite element equation. This part is what we are calculating in the previous slide. This was the global stiffness matrix. We introduced the force, the nodal displacement vector and the force vector, capital F, the external force at the node, right? And I hope you understand why we are not talking of small f. Small f is when we are just talking of finite element equation for us, for a single element. And you find like for a single element, you might not so much concentrate on that. Yeah, in the spring we did that, and in the bar we did that for your understanding. But when we come now to solving the equation, you need to define the boundary condition. You cannot define boundary condition on a single element unless it was a one bar structure, such that if it was one bar structure, so this is just one bar, then this is fixed head, and then I don't know whether it can be free or still fixed. So this is still having one element and at the same time a structure made of one element. So we can define the boundary condition. So in that case now we can have the same the finite element equation for an element, elemental finite element equation being the same as the global finite element equation. So note the difference. And then once we have the global finite element equation, we need to move to the other stage. I don't know whether the other stage, I don't know, we need to introduce the boundary condition because that is the step 5. To introduce the boundary condition, you can look at this structure. This is fixed, and here you have force P. So we know U1 is equals to U2. There is zero displacement that can occur here. And force 1 is the reaction at node 1. Force 3 is the reaction at node 3. We don't know, we can calculate the reactions. But force at node 2 is node P. So then F2 becomes P, U1, U3 becomes 0. And that's why we are saying the step 5, global finite element equation, and you introduce the boundary condition, loads and boundary condition, we are going to have this equation. Our finite element equation becomes like this. So U1 is 0, 0, then F2 is P. So we have introduced the boundary condition. So we are through with step number 5. So now we need to go to step number 6 to solve for nodal unknowns or unknown degrees of freedom. In this case, it's nodal displacement. So let's move quite fast. You can see it's already 9. The presentation should be starting now. But we have to do one to finish this example. So far, so good. I hope you are appreciating how easy it is to deal with this analysis matrix method. I don't know why wonder people are now you're 93. Don't just make the class attendance, especially this one. I'm making it as a disclaimer to the mature entry guys. Please attend my classes. If you don't want to have problems going to failure, attend my classes. I'm having problems with those guys. It's better to be honest and to tell you so that you don't fall in the same mistake that I am having those with failures. Because if you never attend classes, just do a sacrifice. I know you are working, but do a sacrifice. Because some of these concepts, if you come start learning them by yourself, you might I know for me, I've gone through them so many times, but for you, it's the first time. So you may spend a lot of time and then you start revising during the exams. You may not, you have other 8 units. It's not only this unit that you are studying. So you not have adequate time. So I would prefer you attend the class, you understand the concept, then you can read the notes later on. So that number going to 9,000, I'm worried who are those people who are not together with us. Anyway. So to get the step number 6. Step number 6. Solve for the nodal unknowns. Now, if I go back to this equation, remember we said once you have this one, now you can use any method. This is just an algebraic equation. Yes, in matrix form. So you can use any method, row reduction. You can use elimination method. You can use that's the Gauss elimination method, and so on and so forth. Cramer's rule to get the determinant, and then you get the inverse and all that. But the simplest, and you find very handy, it comes in very handy, when you have this, when you have this, now you have introduced the known condition, the known conditions, u2 and u3 in the force, in the displacement vector. So we can say u1 and u3. So you can remove, for now, you can simplify. This is like a shortcut. You can simplify by cancelling the rows associated, the rows and the columns associated with that, the value where the displacement is 0. So this is u1, u2, u1, u2, this is u3, u1, u2, u3. So you can remove the rows and the column associated with u1 and u3 for now. Okay, then you see you are only left with this one, with this element, or the member, the set 3. So this one becomes very easy, because now this is 3 EA of L. Don't forget the factor we have put out here. EA of L is equals to P. Yeah, because we are just multiplying. This one you multiply by all that, you are left with that. U2, sorry. 3 times U2 is equals to P. 3 EA of L is equals to P. Therefore, you can get U2 is equals to P L over 3 EA. So this is a short way. Once you have what is the node or known values, you can first remove or cancel. We can say cancel, in quotes, the rows and the columns associated with that column and row. And therefore, we have calculated step. Okay, I had gone backward. So now we have calculated. Yes, this is why now I was explaining to you why we are saying deleting the first row and column and the third row and column, we obtain this, and therefore U2 is given by P L over 3 EA. And U2 is the only nodal displacement that was unknown. So this is just an answer given, including the other values which you are given. We knew U1 is 0, U3 is 0. So this one you can put it or not. Up to this part. Up to this part, we already have gotten our answer, the nodal unknown value. Step number 6 or 7. Step number 7, we need to solve for the strains, because our problem relates to the strain in the 2-bar element. So solve for the unknown strains and stresses. Remember, you might not be told to, like now our problem here, we are just required to calculate the stresses in the 2-bar element. But you have found that to get to that stage, you have to move through those steps. So you don't have to it's good to have those headings and all that, and to know those steps. But you might be asked a problem whereby it doesn't require you to work all the way up to the end. Like if you are just required to get the nodal displacement, you don't have to come to this stage, because you have gotten your answer at step 6. Now, we want to get what is the stress in this member and in this member. And to do that, remember the note number 2, strain displacement. You may wonder why I was giving it at that stage. The strain displacement relation. We said stress, we defined stress. We defined the stress in terms of strain, Young's modulus times strain, and the strain was defined in terms of strain displacement matrix, strain displacement matrix. So this one B1, U1. And remember, we derived from first principle what is B, it's 1 over L, and 1 over L, U1, U2. So you can get the stress to be here, U2 minus U1 over L, E over L. We have U1 is 0, U2 is. So what is happening here is just now you start opening up this. So this, you just open up the, or you you open up the bracket by multiplying here, and then you substitute the value of U2 and U1. Therefore, you are going to get the stress on member 1 is equals to P over 3A. Same case with stress in member 2. Can you work this one out using the same approach? Can get the same approach here. The value remains the same, the value of P2. And then you are going to get this answer as negative P 3A. Of course, we are not putting the units. They could be in megapascals and all that, and so on and so forth. So we have come to the end of that example. But before we conclude, we said the last step, although it's not asking this question, sometimes it's come in terms of comment on the answer. So that is the step number 8, where we talk of interpreting your results. Okay, so what do you know? What can you read from the result that you have obtained? Number 1, we have found stress sigma 1 is equals to negative sigma 2, or sigma 2 is equals to negative sigma 1. So it shows that bar 2 is in compression. Okay, so this is tension. So in this case, this bar was in tension because there is a pride here, but you see this fixed here and the load is applied here. So bar 2 is in compression. So you understand, by getting the negative value, the bar is in compression. Number 2, you can see the stress in member 1 and 2 are the same. Only the sign is different, and the stress is transmitted equally. And we are talking of a linear bar element elastic. So this is a statement that you need to digest in your system, and remind you of strength of materials. The calculated stress in 1 and 2, they are exact within what you call the linear theory. Okay, and for 1B bar element. That's why I was saying, even if we further divided these elements into smaller or finer elements, we are not going to get more exact solution. We have already obtained the exact solution. The answer you have calculated through the finite element method. If you use the strength of materials approach, we are going to get the exact answer. What is the stress in these bars? So the answer is what you're saying, it's exact. It's a closed form solution, it's the exact solution. So our approximation method, the finite element, it have coincided with from the linear theory, from the strength of materials approaches. Therefore, no need to define or to refine our mesh, to reduce the sizes of our element. You should also note that when we come to tapered bars, we use the average value of the cross section. So sometimes, and I know this one is harder in the strength of materials record here, 2204, 2214. So we may have a bar element like that, and the load is suspended here. So when we come to this kind of analysis, to get the area, we use the average. So maybe you have the cross section here, you have the cross section here, you get the average. That's one we use when we are defining what is K. K is equal to EA of L. So this A, and then minus 1, minus 1, minus 1, 1. So this A is what we are saying is the average. Again, we have seen, for us to get the stresses, we had to go through the steps of getting the nodal displacement. And this is because we are using the displacement-based FEM. If you are using the force-based FEM, remember the direct method. If you use the flexibility method, we would have calculated the nodal forces first, then we get the stresses. But now we need to get the nodal displacement first because we are using a displacement-based or FEM. What we call them, we had two methods, two approaches. One was the direct approaches, the other one was variational methods. And you said you're going to the direct approach. And in direct approach, this is in page number 10 of your note, I believe. We had the force of the flexibility method, and where we said that the nodal forces are the unknowns. And the other method was displacement or the stiffness method, direct stiffness method. So this method, we can also call it direct stiffness method. So where the nodal displacement are unknown. So we first calculate them, then we can start recovering the other values of the unknown. All right. That brings us to the end of that example with the additional materials that we have seen. And I might be now going to the stage of asking questions, but today the question session will be very short, because by 9:30, I believe I should have joined the other meeting in the department. But always remember, even when you are reading the note, use that comment section. Always write comments there. If you have comment content, if you have any question, write it there for the sake of answering to you and answer to other people. And also for the sake of when we have the interaction, this video will be the YouTube will know that there is more interaction in this video and it's useful to other people. So it will be shown to other people, because we believe that when we put this kind of knowledge here, I know you have been watching so many YouTube videos on engineering from India. They have been very active. But now, why don't we have our own here from Africa and all that? Okay, and I know people I can see people are coming up. So when it's being recommended to many people, even the ranking of the university and the country and the content as a whole goes high. So that's why I always tell you to comment, to like, to comment, to share, and so on and so forth. And don't forget to subscribe. It's very important. By the time you are finishing this class, you should have hit how many? 500. I know there are extra 50 people who are remaining to subscribe. If you want to, because there's a time I'll be posting some tutorials, you can activate the notification bell, because once I upload the video, you'll be notified when we have a tutorial. Some of these questions, when I get time, I might create some videos and put them there, even as I share with you. But it will depend. We are going to see. All right. So this is example 2.2. I want you to look at it. It's almost similar to the other. The cross-sectional area is the same, but now we have introduced an interesting part. This bar, there is a gap, a small gap delta of 1.2 millimeter. So you need to determine the support reaction at the two ends. So the support at F, so you are going to get F1 and F3. But remember, for here to have a reaction, this bar have to touch here. So the first step that we need to calculate is, can our force P cause this gap to cross? And then we can experience reaction. So think about that, work it out. These are the probable answers. You can prove me wrong or right. Punch your calculators. Let's see whether you can get these values. And that's the end of our lesson today. Before I open the class to questions, let me see whether we have any question in the live chat. Samuel Durian, you're asking, sir, in K2 matrix, is U2, U3, or UI, U2? Is K2 matrix, is it U2, U3, or Samuel Durian? That question is, it's not clear. Let me see, Humphreys. I think we have forgotten to solve for the reaction F1 and F2 by substituting the values of U2 and U. Okay. That one you can do it. Yes, true. We did not solve that. You can or you cannot. Let's see. What was the question? The question was find the stresses. Find the stresses, right? Now, when we have gotten the displacement, I've gotten U. When we have calculated the displacement here, we got the displacement U2. Then we know from the expression of stress. Oh, you already changed this. Okay, thanks. Thanks, Sam. So, Humphreys, from this expression, why I did not go the step? Remember, when you are solving equation, it's good for your practice. But when you are in class, for example, exam, or when you are solving something, you only need to calculate what is required. So our equation here doesn't need the value of F. So in that case, directly using this equation, you only need to get the displacement, and of course this strain displacement matrix. I believe you can also get the force and use it to get the stress by using F over A. So you can try that and see. Try that and see whether you can use the other direct method that we have been having to do that. Jude Jero, it's U2, U3. Oh, you have corrected that. That's true. Okay. So I'm going to allow just if anyone with another question. I always like, let me exit this one now, the full screen, so that we can do what? Hey, it's not exiting the full screen. Why? Escape. Okay. Let me share with the. Let me stop sharing this so that I can exit this full screen. I want to share the link so that anybody with a live question can ask. So, right. So class lab or only share this live link with people in class. Remember, we try to avoid the spamming. So don't share it here on this chat. Just share it in your group WhatsApp. So I'm posting it to which group? For DS 2021. So if you have any question there, but only log in if you have live question. You have a question that you did not understand. Otherwise, if it's simple question, you can ask it in this chat. So our class heads there. Allow me to just share once more. Share this. And we are here. I want to give you the answers. Probable answers. These are probable answers to the previous exercise for those who have worked them out. Example 1.2, if you did work it out, you should get something like this. Yes. At iPhone, you have joined. So if you have a live question, go ahead. And it's good to put a video on so that we can see who we are talking to. The class rep can identify you. And also, I don't know, by the end of this course, I don't know how many people have known. You just be meeting on the streets and I don't know you. So iPhone, what's your question? iPhone? So you only log in if you want to ask a question, eh? iPhone, any question? Okay, as they join in, the other practice exercise you have there, the answer again, I have given it there. So Nerius Wagari is listening to a radio and is in class. So I'm only allowing people to log in if you have a question that you want to ask. So if I mute you, know that there is a noise from your end. So I mute you. Daniel Kiongo. Okay. So look at those examples. See whether you can be able to get this equation. Good. Daniel Kyogo, welcome. So even after the end of this video, when you are watching it later on and you have a query, you can ask in the comment section. I'll be glad if I can answer that. All right. That brings us to the end of our lecture for today. So you are dismissed. Until next week, I hope you have... the link is delayed. What does that mean? Daniel Kyogo is already here. Some people are logging in comfortably. What I did is that now you cannot just log in directly. I mean, when you log in, I have to admit you. I'm trying to control so that we don't have a case of spamming. Kiongo, if there is no question, I'm going to move you out. Daniel Kiongo. Losh. All right, all right, all right. Just hold a second, sir. Humphreys, you have a question? Okay, it's open. Just click the link. It will come direct to here. I have an important question. This is Humphreys. Yes. Login. Oh, you don't have YouTube. You have sorry, Zoom. You have to have Zoom installed to join Zoom link. Okay? So look at that example. In your note, I have given page 46. Maybe let me share a blank whiteboard. You may have a case whereby Mure admit TRRR. I'm not going to admit you. That is not our name. Somebody TRR. Please use a professional. Serious. I'm not being malicious, but how do I differentiate you from a spam? Actually, I tell people to log in using their. I don't want you to tell you to log using your registration number, but again. Okay, Murray, unmute yourself. Murray, unmute yourself.
Hello.
Yes, Murray. Go ahead.
This is the question I had.
Yes.
I attempted the question you left last time, and I just want confirmation. I noticed, I don't know, maybe I made a mistake, but I noticed if you name the displacements differently from how the answer you've given us are, like if, for example, you're U1, if you could display your screen so that I can.
Oh, okay. All right. I had shared a different screen. Let me stop sharing this. Sorry. I'm on screen sharing. Just a minute. So share screen.
Yeah, thank you. I'm saying, like, for example, what you named as U4, I had as U1, and what you named as maybe U5, I mean U3, mine was U4. So I noticed that depending on how and mine, the combinations of the matrices are the same, the cells, but where they're located was changing slightly. Is this correct, Ama?
Yeah, that's right. Because if you have like this one, this is Nodal. Let's say, for example, you have I want to annotate. Let's say like you have this as node 1, 2. No, okay, let's say this is node 2, 3. This node 3 now will be shared between this element and this element. So it means it will be different, like when this node 3 is shared between this element and this element. So it's correct, it's true. That's why I had fixed these nodes so that we can try to come up with them a same answer. But you may find like when we start now working out the real problem with actual values, you may find like the answer when now you put the numeric values, you may find like the matrix becoming the same.
Oh, okay. Okay, thank you.
All right, thank you. Daniel Kyogo, Franklin Alepa. Any other question? All right. So yeah, something I wanted to add when I was sharing the screen. I wanted to get a blank. Sometimes, yeah, stop sharing this. I wanted to share whiteboard. Then you can minimize that. So this, we have a bar Okay, undo. Let's have a bar like this. Then let's say there is a uniformly distributed force. Okay, this is node I or 1, node J. So let's say the uniformly distributed like Q, maybe Newton per meter or Newton per meter length. So this is Newton per meter. Or we can have a 3 node. Okay, have a 3 node. Maybe we have node here, a node here, and a node here. Then again, let's say we have, okay, this is L. Okay, this is L. So if we introduce a node at the middle, and then this becomes L, and then this is middle here. So again, we assume a uniformly distributed load throughout. So we consider this to have this type of uniformly distributed load. Assume a bar element that is suspended like that. And then we have maybe a system, the one that's supporting the load, is attached here. It's attached here. Maybe now it's carrying some weight. So you can assume maybe it's clipped here, 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 here. So we can see maybe we might consider this to be uniformly. It's not just applied at this node. So it's uniformly distributed along the length. So in this case, we have to resolve the UDL into nodal forces. So if it's just like this one case here, so we know the load that will be applied in this head will be, the total load is Q times L. So in this head is QL over 2, and in this node is QL, and in this node is QL over 2. Okay. So this will be QL over 2. That node and the node here is QL over 2. And from that, we can say we have resolved our forces here to know the forces. Now, like in this case here, of course, the same thing. So half of this will be carried in this node. And then this half will be carried in this node, and this half will solve to this node. So in this node here, this will be, of course, we are assuming this is not L. Okay, you can take it in any way. But let's say these are 2 elements. Let's say these are 2 elements. We have added another element here. We have added another element here. So it means, assume they are same length. So we assume that this is length L, this is L, and this is L. So, and this is a node here, and a node here, and a node here. So it means now, and we have a UDL applied uniformly along the length of that member, Q. So we resolve this. Of course, the total load is, for this length from here to here, we have a half L, so this is L. So at this node, you have QL. As this node L is, this part is L over 2. So the head here, the resolved node of forces here will be, this will be QL at this node. So you have a force QL applied there, and a node of force here, QL over 2, and a node of force here, QL over 2. So that's how you resolve when you have distributed loads. You convert it to equivalent nodal forces. All right. Thank you. So, Kiongo, did you have a question? TRR, allow me to remove you because this TRR with so many R's. Daniel, Kiongo, any question? So, okay, that's it. That's for now. Class dismissed. You can leave at your own leisure. I'm going to close this. We meet next week. Bye-bye for now. I hope you are enjoying the class. So I'll stop sharing now. And I'm